Hello, my name is Khumouyn Jabbarkhanov, and we're starting the podcast. And I'm very, very excited to begin this interview with Professor Martin Heyer, one of the influential mathematicians of our time. And he is a Fields Medal owner, and he is known for his groundbreaking work in stochastic partial differential equations. And he's our guest today. And it's great honor to speak to you today, Professor, here at the 15th ISAC Congress in Kazakhstan.
Pleasure to be here.
Okay. And our first question is, of course, it's just to say welcome to Kazakhstan, welcome to Nazarbayev University. And the question, is this your first visit here? And what are your first impressions of the country and the ISAC Congress so far?
Yeah, it's my first visit to Kazakhstan. It's actually my first visit to Central Asia.
Wow.
So I've never been to this region before.
Mm-hmm.
So far, I've had a very good experience. People have been extremely pleasant and very nice. And was quite impressed by the facilities and by the university, which is you have a really nice setup here. I think the conference has been really good so far.
Okay. So good to know that you are enjoying on this conference. And I was wondering about your life and your career. So as we already know that as a teenager, you already were successful in software, right? The development in these coding things. And I was wondering, and also you had experience in physics, in PhD and so on. So how did your journey into the mathematics begin alongside that? Was there a particular moment or person who inspired you early on?
Well, of course, my father is a mathematician, so I've always seen mathematicians around at the house. And I've always had some interest in mathematics. But then when I was a teenager, I had interest in, basically all the sciences. So I was also very much interested in physics and sort of technology in general and programming. So when I started my university studies, I didn't really know, I was hesitating between mathematics, physics, and computer science. So I didn't really know which one of the three to choose. And then my reasoning was that I already knew quite a lot of programming, so I had the impression that in computer science I wouldn't learn as much. And then I thought my father is a mathematician, so then maybe I shouldn't do mathematics. And so I went into physics. But then, so in physics, I liked physics. I still like physics very much. But I was always attracted much more to theoretical physics, so I was not very good at lab work, right? Of course, in physics, a first, second year undergraduate student, you have to do some lab work, very basic kind of little experiments, which I kind of enjoyed, but it was not, it didn't feel, in some sense, I didn't really feel like I was in my element. I felt much more comfortable with the theoretical aspects.
No.
And then I was kind of then more and more drifting towards mathematics. So during the studies, of course, I sort of chose. We could choose between different. Like in the third year, there were many elective courses, and so you could choose between different tracks, and one of them was theoretical physics. So of course, I chose theoretical physics, and then I followed quite a lot of mathematics courses. I actually did a mathematics degree kind of at the same time, so I followed many of the mathematics courses, and then also mathematical physics. And then I always felt like, if I write a paper and I, come up with some result or something, and I put my name to it, and I sort of, put it out there and say, I believe that this is correct, then I want to be 100% sure that it actually is correct.
Yeah.
And then basically I realized that this was only possible if I was actually doing mathematics, right? If I was really giving mathematical proofs, and not, just kind of hand-waving arguments. And so that's why then basically I moved more and more towards mathematics.
Yes, I can also imagine that, because I'm also enjoying on this proof process. I could also choose some directions in mathematics, but on the proof way, when you structure everything, yes, this is something different. Then the next question, particularly, of course, we know that you are working on stochastic partial differential equations, right? And especially about KPZ equations involved in your research, mostly, I can say.
Not really mostly,
Mostly,
but I did some work on that.
Okay,
yeah, that's right.
Yes, that's fine. Sorry. In this direction, in general, in stochastics, so why this kind of ideas are you working on in stochastics so important in science in general, and even in everyday life here? Can we say so?
Well, I think some of the ideas are closely related to, or some of the mathematical problems that show up are very closely related to problems that also show up in quantum field theory. So they're actually really old problems that people realized in the late 20s, like the late 20s of the 20th century, so almost 100 years ago, when people tried to build quantum field theory. Rightly, it was the beginning of quantum mechanics. And so after developing classical quantum mechanics, then people wanted to develop quantum field theory. And they realized that you have these infinities that kind of show up. So you have infinitely large predictions which make no sense. And they started to come up with various techniques in order to deal with these infinite quantities. And in these stochastic partial differential equations, you have a very similar problem, and it's also mathematically very similar. So you have these infinite quantities that show up because you look at some idealized mathematical model. So of course in reality there are no infinite quantities, right? So in reality the quantities you look at are finite. But in the natural mathematical models that you would want to write down to give an approximate description of reality, there you do actually have these infinite quantities that show up. And so you want to understand why these models still make sense and why they do actually give finite predictions, even though it looks like you have these infinite quantities in them, right? And so I think that's a very kind of interesting area, which, like, it's sort of a little bit at the frontier also between mathematics and physics, because it's a problem that was first realized by physicists, right? And then physicists came up with various ways of dealing with this, and then mathematicians picked that up. I think I kind of used this in probability theory, where it was not so much exploited or realized that this, showed up naturally before. I mean, it was realized, but people didn't really know how to deal with it, except in some special cases. So there was some pioneering work from maybe 20, 25 years ago. And so, I worked quite a bit in this kind of direction.
Okay, that's interesting. And the next question is, so in the process, when you work in science, in research, when you do this, all of this stuff, so we know that these concepts are quite difficult. I mean, difficult as a concept, as a problem. And do you rely more on, how do you work in general? So do you rely more on creativity, on collaboration, or step by step? So what's the secret of the success?
Well, okay, I don't know if there's never really one cooking recipe, so how that works for everybody. But I think, I rely quite a lot on intuition. I mean, you try to get some kind of intuitive understanding of what are the fundamental mechanisms that sort of make the problem tick in a way. And then once you've understand the fundamental mechanisms at some intuitive level, right, then you can try to make it more and more precise. And so in some sense you go like top down. So it's really not, you don't build proofs step by step, right? Like once the proof is built,
yes,
then it is presented in a way that is somewhat step by step, right? Because
yes,
the proof, you start from the statement and then you have a number of logical steps and you reach somehow the conclusion. But that's not how you get to the proof, right? So the way you get it is much more of a top-down thing, where you sort of try to first get some intuition, you try to have some broad overview of what could be, you know, the big step that gets you to that proof. And then you say, okay, of course, the argument makes not really sense because you've neglected lots of things, but you sort of try to get the essence of the argument, right? And then you kind of refine it. And you say, well, actually, if we could get to this intermediate step, then we could maybe do it in two pieces. And then you try to aim for that intermediate step. And then again, you see what is missing. You try to identify the things that are missing. What are the key pieces that are missing? You try to first understand these and then fill in the details and so on, right? So it's really much more like this, where you somehow try to find intermediate steps and intermediate goals. But you always first try to get some kind of high-level understanding at the intuitive level, and then you kind of fill it in. And, you know, once you, at some point, you've sort of finished filling it in, right? And then the proof is complete.
Yes, very, very interesting point. I can agree with you. Yes. Also, I think the time is a little bit changing in my point of view this time. I mean, if you let's imagine, say, you were starting your PhD right today, for example, with everything happening in mathematics and the science in general, which direction or topic would you choose to work on? So today, if you start.
It's a very difficult question.
Yeah, I know.
I mean, it's quite possible I would still choose mathematics as an area of research. I think this is something, I mean, either mathematics or maybe medical research or something like this. So I think there's going to be also a lot of disruption from AI and so on. So I think that's going to have a lot of impact in medical research, also, you know, developing medication, that kind of thing. And of course, that's also a very important area. On the other hand, I really like kind of understanding things, and I think for this, still mathematics is somewhat unique.
Yes,
it's
I agree.
It's really the really kind of course, theoretical physics is also, right? In theoretical physics, you also have a very thorough understanding. It's not quite at the mathematical level. It's not as precise, but it is more conceptual, and you have also sort of very interesting and sophisticated concepts to understand. So I think I would still go kind of either in mathematics or theoretical physics.
Okay. That was very interesting to me. The next question: what advice would you give to young students and early career researchers from smaller or, I don't know, developing countries, maybe like Central Asia countries like Kazakhstan, who wants to do serious work in mathematics?
I think it's probably quite important to try to find in some sense also like the problems that the mathematical community is interested in, right? But that are still somewhat accessible to you, because there's at the end of the day, mathematics is, okay, there is a somehow, it's kind of an abstract Platonic world of mathematics that is somehow, in some sense, almost disjoint from humans. But at the end of the day, it's a human endeavor, right? And there is a sort of global community of mathematicians, and, you know, people interact a lot, so, you know, at conferences like this one. And so there is usually some sort of a shared understanding of which problems are interesting problems, and which problems are maybe technically difficult but actually not so interesting because they maybe don't have a broader impact. And so I think it's important to, you know, try to get some understanding of this, and to you know, discuss with people from different countries, and maybe get some contacts with people in, you know, in different countries, and also travel during the, you know, either during the PhD or after the PhD as a postdoc, do a postdoc abroad, and discuss with people, and, you know, like just to get the feeling for, in some sense, right? You see, like the atmosphere of the community, or like the thinking of the mathematical community.
Yes, I agree that the community in mathematics is quite important. Yes, with this sense. Okay, the next question is how important are the international events like ISAC, which connects the researchers and sharing the ideas across the cultures? So. How important this is for you?
Well, I think it's very important for two things. So the first one is, of course, you know, nowadays when people prove some result, they put the result on archive, and so everybody can see it immediately.
Yes.
So in some sense, in the old days, there was the aspect of advertising the results or disseminating the result, which in some sense is slightly less important nowadays because the results are immediately available for everybody to see them. But it's still very important for two main aspects, I think. So the first one is, you know, to actually learn the main. Remember, as I was talking just earlier on about, you know, how you build the proofs, right?
Yes.
And when you see the paper, when you have the finished product, what you see is the last step, right?
Yes.
So what you see is somehow all the little steps that get put together in order to build this big proof. And it takes quite a, if you just take an article like this, and you really, I mean, usually if the article is well written, then of course the person tries to explain in the introduction what are the key ideas and what are the big steps. So to try to actually explain the whole process and not just the finished proof, right? So usually that's what people do in the introduction, or maybe the first 2 or 3 sections of a paper. But somehow it's still the case that it's much more efficient to explain this via a conversation than by actually writing it all down and then reading it, right?
Yeah, I'm agree with you.
So, you know, you see a 100-page paper, even if the introduction is very well written and so on, I mean, it will take you weeks or months to really understand what's going on. Okay? But if you can just talk to the person, you can spend, you know, half an hour talking to the person, and you can understand the key ideas and the key steps of the proof, right? And so for this, it's really important because it's much more efficient way of communicating ideas by just having a conversation than by writing it face to face. So you have the interactive element, right? That you can say something and then you see immediately if the person understands, then you go much faster, or you know what they already know and what they don't know, and so you can focus on the things that they don't know when you do the right. And whereas if you write it, well, it has to be for everybody. Right? Like it's not custom
Yes.
custom made for the person that you're talking to, right? And so then it's much less efficient. And I guess the second related aspect is still the community part, right? Like to just meeting up with people, just to kind of know who is around, know, well, like I was mentioning earlier, sort of like know what people are interested in, know what's going on at the moment, what are the problems that make people excited, and also just meet and talk to people, so then you have some kind of personal link to a person. Then it's much easier than to write them an email if you have a question or something,
Yes.
right? Like if you've had a chat before.
Yes, I agree with you. And also I would like to add also that sometimes when you attend to the conference in this way, and when you attend to your session, your particular session, you feel like you're in a family,
Right.
because you are with people who know, right, who are known in your field, and you know them, and you read their papers, and but you have never seen them because you just know their names. Oh, that guy is here. Oh, that guy is there. And you see them, and sometimes, for me, I don't know, just sharing my feelings. Sometimes working in this, in the office every day with this routine, sometimes I feel like I'm alone in this world with my problems. But when in the attending in this kind of conference, I see that I'm not alone. So we have at least 10, 15 people who are working in the same kind of problems, right? So that's actually very interesting, and very happy to see you here today, actually. And the closing question, maybe just your, I can say, message. What would you like to say to the young generation watching this interview, especially young people in Kazakhstan, of course, who are passionate about the mathematics and science, say that they're excited, they're starting, and they're going to see this interview, and your message to them?
Well, I think one thing that's kind of important is to actually do the things that you like rather than doing the things that you think will be liked by other people.
Yes.
You see what I mean? Right? So it's not always a good idea to somehow, just take the latest hot subject, which is currently kind of the hottest topic, and then say, oh, this must be the most important thing, and so I'm going to do this, even if I don't really find it that interesting or I don't like it that much, because at the end of the day, I mean, especially when doing mathematics, you can really only be successful or good in a topic when you actually like what you're doing, right? And also you can, if you didn't really like it, you're not going to kind of invest somehow, make so much of an effort or really invest so much of yourself to kind of try to figure things out, right? And so I think it's really important to actually do the things you like somehow, rather than
yes, of course. So thank you very much, Professor, for spending your time with us. It's really honor for us, for not only me, not for people who are watching, for our community, for Nazarbayev University, for our Kazakhstan. Thank you for coming to this country. Thank you for coming for the Central Asia in general first time, and I hope you're gonna enjoy in the following days of this, in the following days of the conference. I mean, and thank you, and see you later.